Hello everyone, my name is Bhusan Chettri and I'll be presenting our work titled The Clever Hands Effect in Voice Spoofing Detection. So in this talk, I'll be talking about introduction and motivation. Then I'll discuss briefly about the goal and contributions of this work. Then we'll be looking at ASVspoof 2017 benchmark. Then we'll take a look at 2019 ASVspoof PA benchmark. And then we'll talk about the conclusion and future work of this paper. When a system produces excellent results using cues that have no relevance to the actual problem, such an effect is called the clever hands effect in machine learning. The term actually comes from the real-life example of clever hands, the German horse that appeared to solve basic maths problems. However, it was found that this horse was doing this computation by actually learning to respond to irrelevant cues that was confounded with the correct answer. In this work, we study two popular anti-spoofing datasets, ASVspoof 2017 and ASVspoof 2019 PA, and demonstrate how spurious correlations in training data result in improved detection performance. We do this by using our simple framework for detecting the clever hands effect as shown in this figure. And we demonstrate its efficacy on two popular benchmark datasets using a well-established anti-spoofing model called LCNN. Furthermore, we demonstrate that this effect is not model specific by using a separate neural architecture. The main goal of this paper is to raise awareness of this effect on these two datasets. And therefore, removing such a horse effect is crucial towards design of reliable and trustworthy solutions on these datasets. So in this figure, we illustrate the pattern difference between bona fide class and spoof class. Here we can see that majority of bona fide files in this dataset contain non-speech in the start, which is not the case with the spoof version, where we see speech samples in the start. So within this non-speech samples, we often find burst click sound appearing in the start, as can be seen in this diagram. So the hypothesis here is that BCS, which is a recording artifact, serves as a strong cue for bona fide class because this click sound does not appear in spoofed files in this dataset. Now, to understand the effect of BCS artifact, what we do is we simply remove this artifact from test samples and rescore them using the same model. And we want to see how this intervention affect the confidence score. So we do this across all the phrases of this corpus, S01, S10, and we pick examples from all training, development, and evaluation sets. As can be seen from this table, there is a substantial drop in confidence score, indicating strong correlation of this click sound and model decisions as we anticipated. So this table over here shows the results of intervention experiment, where we are basically trying to unmask the clever hands effect on this data set. So the first row over here, by non, this means initial model performance without any intervention. So for clarity purpose, we have repeated the same column over here because FAR, false acceptance rate, and false rejection rate, they are same, they're equal to equal error rate. So we see the same column, we just copied it. And we did not have the training results for TDCF. So this is not applicable. And likewise, we have for small CNN model. So basically this BCS removal. So we have identified samples that contain this BCS artifact. Now what we are doing is we are basically removing those artifacts from these test samples and we are performing the evaluating the performance again, basically. So you can see how the number changes, how the error rate on the training set jumps from 0.0 to 0.19, likewise on the development set and evaluation set. And similarly, the same trend we see on the another model, small CNN. So this results clearly suggests that BCS has a strong impact on the model decisions. Now we confirm this using an independent experiment where we now try to manipulate the decision of this model using this burst click sound as a signature, because here we have identified that BCS serves as a bona fide class signature. So now let's take this signature and replace the first 100 millisecond samples from all the correctly detected spoof samples. So basically we're taking true negative sample and appending this signature with the hope that now this spoofed samples will be misclassified. They will be able to fool the system. That is what we are trying to do. And as a signature, we take this 100 millisecond sample from this audio file that has been confidently classified that contains the artifact. So after this, we plot the score distribution in order to see how the influence has happened. So as we can see, the blue and orange plot shows the initial and new score distribution. We do this for the development set and evaluation set for both LCNN and small CNN models. So it is quite evident that the model gets highly influenced with this BCS artifact, as can be seen from the change in the score distribution. Now let us take a look at the ASVspoof 2019 PA dataset, and this slide basically shows the influence of silence. The hypothesis in this dataset is that the trailing silence duration serves as a strong cue for spoofing detection. As we can see in this figure 1, which illustrates the average trailing silence distribution across different attack conditions and the bona fide class, we see that there is a clear discrimination in terms of the duration. And this also suggests that this line, dotted line, can be used as a decision boundary. So with this statistics, what we can do is we can simply have a simple if-else statement as such. If silence is greater than 0.1, let's classify it as spoof, else it is bona fide. And doing this simple computation, we can get 100% classification accuracy from this statistic itself. So this strongly suggests that this dataset has got issues, and this silence served as a very strong cue. To further elaborate this, we train a simple multi-layer perceptron using a scalar input, that is average trailing silence duration. We use a single hidden layer with just 10 units, and we train this model for fixed 20 epochs using ReLU and 20% dropout. As can be seen, we obtain equal error rate of less than 20% using just one scalar input on all training, development, and evaluation set, which is way better than performance from a random classifier. Furthermore, we can ask one question. So how does the model behave when it receives an input comprising only silence? So in order to answer this, we took a test instance example. We replaced the audio content by silence, pass it to the model. So what we achieve is we received, the model now classifies that instance as spoof with more than 90% confidence. And we repeated this for every instances, we see the same result. So this suggests strong correlation of the silence with the model decision. So next, what we are trying to do is we want to understand in how this silence can be used to perform various intervention experiment. So this table shows the result for different interventions that we perform on this data using these two different models. So the first column over here shows the original experiment where there is no intervention. The second row denotes test time intervention, which means we remove the silence from the test utterance only at test time. So the other one, TS train, this denotes intervention during training only. So this means we keep the text files as it is, but we train the model by removing the silence distribution, the trailing silence distribution. And the last one is we do this intervention at both training time and test time. So this is what should be the case actually. So as we can see, for each of this intervention, we see a sharp increase in the error rates. This is to be compared with this row. And this holds true for both the metrics, equal error rate and TDCF. And this holds true for both the models, LCNN and small CNN. The trend is similar. We see increase in the error rates. Now, next thing what we want to do is we want to see if we are able to use this silence duration as a signature in manipulating model decisions. So what we do is we take the spoof file, which is this one, from the training set that has the longest silence duration of 1.65 seconds. That is this 26434 samples are pure zeros. So what we do now is we replace this number of samples of each audio file. We do this on the entire data set with 0. We just replace them with 0 during test time. And we now plot the score distribution of the original settings. This is the blue curve. And we can see how the score changes dramatically, the peak over here, which suggests that the 1.65 seconds of data has got strong impact in the decision making. The silence has got a strong impact. Likewise, we can see a similar trend in the evaluation set, and the trend shows similar pattern for small CNN model on both the data sets. So this strongly confirms our hypothesis about silence being a strong cue on this ASVspoof 2019 PA dataset. So to summarize, data confounders or data artifacts are often overlooked in research because the evaluation metric used is often a scalar, for example, equal error rate. And such metric cannot account for what the model has learned from the data. And most of the published work has focused on improving numbers because of the fact that whenever a new model is proposed or used on a data set, if that model is not able to improve the existing performance, then it's hard to convince the reader and get your work published. So this is quite a trend that we are aware of. But then this kind of results often calls into question the trustworthiness and reliability of the systems, because these models has been highly influenced with these artifacts that we have shown in the previous slides. So to summarize, the BCS artifact serves as a strong cue for bona fide class on the ASVspoof 2017 dataset, and silence serves as a spoof class cue in the ASVspoof 2019 PA dataset. The longer the silence duration, higher is the spoof class likelihood. We have demonstrated that such an effect is not model specific, and any data-driven algorithms are likely to exploit such biases if not taken care of explicitly. So one of the limitations of our proposed framework is that there is a significant involvement of human in terms of metadata preparation. So as a future work, we want to automate, provide automatic methods using machine learning to create this metadata preparation. But of course, for that, there will be some degree of human intervention because we need to analyze some of the confidently classified files to understand the kind of artifact that could be there. And then we could use this knowledge to build an automatic system for detecting such artifacts from the data. Because analyzing each and every audio files by human is not always possible because of the amount of file size. The number of files in training set usually is quite massive. So again, on the ASVspoof 2021 evaluation, we have found that this evaluation has made use of new test sets, but the training and validation data comes from the ASVspoof 2019 PA. And the training validation data is used with silence, the work which we have already demonstrated in this work, which has clearly shown how heavily influenced the model gets with this silence when it is trained with silence. And majority of published work, they don't apply VAD because obviously non-speech regions carry significant spoof information. But in this work, we have shown that because of the way data was collected, there is a significant difference in duration, which is picked up by the model as a cue for spoofing detection, which shouldn't be the case. So this means that the horse effect we reported in this work may still exist in this edition as well. So the key question that arises is, are systems reported in the 2021 evaluations trustworthy? So as a future work, we aim to analyze the test data and also some of the top models of the 2021 challenge. Thank you very much.